So welcome to the technical paper session, Camera Control and VR. Our first presenter is Mike Roberts, and he's going to talk about generating dynamically feasible trajectories for Quadrotor's cameras. The paper is with Mike Roberts and Pat Hanrahan from Stanford University. So I just heard that he was still rendering like the last frames on stage, so we'll have some really last-second, cutting-edge research to see. All right, there you go.
Hao, thanks so much. You gave away my secret. Okay, should wait for that. Okay, perfect. So, Quadrotor cameras are everywhere. They have recently emerged as a powerful platform for executing free-form camera movements in the physical world. Here's one of my favorite examples, showing the kind of dramatic shots that are possible to capture with Quadrotor cameras. Notice how the camera moves rapidly and smoothly to reveal this complex environment. Quadrotor cameras are also becoming easier to use. Interactive shot planning tools are emerging that remove the need to fly quadrotors manually using joysticks. These tools enable users to set up shots ahead of time in a virtual environment, and the shots can be captured autonomously afterwards. But there's a problem. Quadrotors have physical limits that constrain their motion. For example, each quadrotor propeller can only generate a limited amount of thrust. Also, quadrotors typically have a top speed imposed by their internal control software. Existing shot planning tools do not automatically enforce these physical limits. To see why this can be a problem, let's have a look at a typical shot you might set up using one of these shot planning tools. This shot seems innocent enough, but the shot could be quite dangerous to execute depending on the timing of the shot. This is because quadrotors execute trajectories by maintaining a desired position they're trying to get to. Let's draw that with a pink dot. And let's draw the quadrotor's actual position with a blue dot. When the desired position moves within the quadrotor's physical limits, we can faithfully execute the trajectory. No problem. But when the desired position outpaces the quadrotor's limits, then we have a potentially serious problem. In this situation, the quadrotor will cut corners to try to catch up and could easily crash into this building or something else in the environment. Or, if you're lucky, your quadrotor has some kind of reactive obstacle avoidance system and will be able to dodge the building. But even then, you're not going to get the shot you wanted. Generally speaking, any virtual shot preview you see in one of these planning tools will be accurate only if the shot is within the quadrotor's physical limits. We refer to such shots as being dynamically feasible, and this talk is all about generating dynamically feasible shots. Stated more concretely, our goal in this work is to enforce physical limits when designing quadrotor camera trajectories. We want the trajectories we come up with to be as close as possible to a user's intended trajectory. And we want our method to run fast enough to use interactively. Our approach for enforcing physical limits begins with a shot designed by a user. Here we're showing the shot's path through space on the left, and we're showing the shot's progress along that path as a function of time on the right. We refer to the 1D function that specifies progress over time as a progress curve. Now, suppose this shot is infeasible, because there are some parts of the shot that require too much thrust. Our approach will be to keep the spatial layout and visual contents of the user's shot intact. Instead of changing the spatial layout, we will retime the existing shot, perturbing its timing as little as possible while remaining within a quadrotor's physical limits. As we'll see later in this talk, our choice to only perturb the timing of a shot will lead to a well-behaved optimization problem that can be solved at interactive rates. To see the approach we came up with, let's have a look at our algorithm running interactively. This demo will be running inside of our shot planning tool, so I'll give you a quick tour of the UI. We show the quadrotor's progress curve on the lower left, and we show the feasibility of the shot in a set of plots on the right. These plots show dynamical quantities like thrust and velocity as functions of time. We draw the physical limits of the quadrotor as horizontal red lines on these plots. In the preview windows and on the quadrotor's progress curve, we color each region of the shot according to whether or not it is feasible. Blue means feasible, red means infeasible. So basically, we want our method to produce shots that are all blue. because if a shot is always blue, it means that the shot is always within the quadrotor's physical limits. Let's begin by setting up a typical shot. As we're adding the first few keyframes, this shot is feasible. We can see this on the quadrotor's progress curve. However, when we add another keyframe, the shot becomes infeasible because there are parts of the shot that require too much thrust and too much velocity. We can see these violations on the feasibility plots. Our algorithm automatically converts this infeasible shot to a feasible shot. We invoke our algorithm simply by clicking the Optimize button. By looking at the optimized progress curve and feasibility plots, we see that our algorithm has perturbed the timing of the shot to respect the quadrotor's velocity and thrust limits. Adding another keyframe makes the shot infeasible again, but we can simply rerun our algorithm in a second to convert the new infeasible shot back into a feasible shot. Notice that the optimized shot is briefly at the quadrotor's thrust limits and is also at the quadrotor's velocity limits for sustained periods. Okay, in this part of the demo, we'll optimize the shot I showed at the very start of the talk. Notice how this shot is not even close to feasible. The middle of the shot requires almost 3 times as much thrust as our quadrotor can deliver and 3 times as much speed. And yet, with a relatively modest change to the shot's timing, we can bring it back to within our quadrotor's physical limits. Because we are explicitly enforcing feasibility, the shots generated by our algorithm can be captured safely and accurately with a real quadrotor camera. Here's the same shot I showed on the previous slide. On the left, we see real video footage of the feasible shot generated by our algorithm, and on the right, we see the virtual preview from our app. And this concludes the demo. Okay, our approach is enabled by 2 distinct contributions. Our first contribution is an analysis of the quadrotor dynamics along a fixed path. This analysis gives us a closed form expression for quadrotor thrust in terms of progress along the path. Our second contribution is a fast method for optimizing a progress curve subject to limits on quadrotor thrust. For this second contribution, we use our closed form expression for thrust as a constraint in an optimization problem. So, in this sense, our second contribution is enabled by our first. And in the interest of time, I will only consider limits on thrust in this part of the talk. However, in our paper, we also consider limits on velocity using these same ideas. Okay, let's have a closer look at those quadrotor dynamics. In this analysis, we're going to leverage a very useful property of quadrotors. Suppose we are given a trajectory through space as a function of time. It turns out that we can compute the thrusts required to follow the given trajectory in closed form. And this closed form expression for thrust is pretty darn useful. In our SIGGRAPH Asia paper, we used it to notify a user if her shot is infeasible. In the work of Mellinger and Kumar and Bry et al., they used this same closed form expression to optimize the time allocated to the individual spline segments of a trajectory. In this work, we will reformulate this expression and use it in a novel optimization problem. This will enable us to get nice and close to the user's intended shot by continuously optimizing its timing rather than optimizing at the granularity of spline segments. To proceed, we make the observation that a trajectory can be thought of as a path composed with a progress curve. We show in the paper that we can still compute thrust analytically using this alternative trajectory representation. In the work of Van Luke et al., they make a similar observation for a planar 2D quadrotor and use it to minimize the time taken to reach a goal. In our work, we extend this analysis to 3D and use it to match a given progress curve as closely as possible. From here, we make the observation that we can pre-compute the contribution of a fixed path in our expression for thrust. And at this point, we've expressed quadrotor thrust in closed form and entirely in terms of a progress curve. This closed form expression enables us to optimize a progress curve while enforcing limits on maximum thrust everywhere along the resulting trajectory. Okay, so now that we can enforce limits on thrust, let's have a closer look at how we formulate our optimization problem. We assume that we are given as input a fixed path and a progress curve. We assume that the input is infeasible. So we formulate our optimization problem to produce as output a feasible progress curve. In our optimization problem, we would prefer the output progress curve to be as close as possible to the input progress curve. So we would prefer an output progress curve like this, instead of like this. We also want to remain within the quadrotor's physical limits, so we use the expression we derived earlier as an inequality constraint in our optimization problem. We encode our preference for being close to the input progress curve with a simple least squares objective. And that's it. This is the problem we're solving. It really is as simple as that. In the interest of time, though, I'm intentionally leaving out a couple of details. In particular, I'm not describing how we represent the progress curve being optimized, nor am I describing how we measure distance from the input progress curve. For more details on these modeling decisions, see the paper. And at this point, it's worth pausing for a moment to ask ourselves the question, why would we expect this formulation to be fast? And to address this question, I think it's helpful to draw a cartoon of the underlying optimization problem. Recall that our problem has a least squares objective, so the function we're trying to optimize has this well-behaved bowl shape. And because we're only optimizing a progress curve rather than an entire trajectory, all solutions will satisfy the nonlinear quadrotor dynamics implicitly. In other words, we don't need any extra constraints to enforce the quadrotor dynamics. But only some of the solutions will respect our thrust limits. In fact, there is an irregularly shaped region of solutions that respect our thrust limits, which I'll draw with this gray blob. So, our formulation has not gotten rid of the nasty nonlinearities in the quadrotor dynamics, but we've moved these nonlinearities into our inequality constraints on thrust. And it turns out that this problem transformation will allow a solver to make very rapid progress towards an optimal solution. The intuition here is that for the first few iterations, our optimization problem is pretty smooth sailing. The constraints are effectively inactive, and a solver can make very rapid progress towards the constraint boundary. Eventually, these constraints do become active, but by then the solver is already very close to an optimal solution. So what about space-time constraints? Space-time constraints is a well-known method in computer graphics for animating complex systems like articulated characters subject to physical constraints. This same method is also very common in the robotics literature, where it goes by the name of direct collocation. However, the well-behaved problem structure we see in our formulation is not present in space-time constraints. To illustrate this point, let's have a look at the cartoon for the space-time constraints problem. In space-time constraints, we also typically have a well-behaved objective. And because we express our thrust variables explicitly, we can express limits on thrust with simple linear inequality constraints. So far, so good. Space-time constraints is looking pretty darn clean. But in space-time constraints, we represent system states and thrusts explicitly. So we must explicitly enforce the constraint that applying a particular thrust from a particular state needs to get to a particular next state. So we end up with highly nonlinear equality constraints to enforce the quadrotor dynamics. And this formulation ends up asking a lot from a solver. Indeed, a solver has to make progress optimizing the objective while also remaining on a highly nonlinear equality constraint. And the only way a solver can do this is by taking many small steps. So, let's summarize the main differences between the two approaches. In our approach, we enforce the quadrotor dynamics implicitly, and we enforce thrust limits with these nasty inequalities. In space-time constraints, we sort of do the opposite. We enforce the quadrotor dynamics with the nasty nonlinear equalities, but we can enforce thrust limits with well-behaved inequalities. As we'll see in the next part of the talk, our approach enables us to find optimal solutions very quickly in practice. And on that note, let's check out some results. We evaluated our method on a data set of 8 infeasible trajectories designed by novice and expert users. We obtained these trajectories from a user study in our SIGGRAPH Asia paper. We optimized these infeasible trajectories to be feasible using our method and space-time constraints. We solved the nonlinear optimization problems arising in both methods using the commercial solver SNOPT. And we used all the default SNOPT error tolerances and parameters in all our experiments. We implemented both methods from scratch, and we took care to structure the implementations as similarly as possible. We also compared our method to uniform time stretching. Uniform time stretching is an inexpensive but overly conservative strategy for enforcing feasibility, especially for long trajectories that are only briefly infeasible. Here we're showing the progress curves generated by our method and uniform time stretching for the infeasible input progress curve shown in red. Because our method is able to non-uniformly perturb the timing of an input trajectory, we found that we could get much closer to the user's original intent than uniform time stretching. We also found that our method was between 25x and 45x faster than space-time constraints. Our method ran in under 2 seconds for all the trajectories in our dataset. We performed all of our timing experiments on my laptop. And we obtained this result when we discretized each trajectory at a moderate resolution of 100 time samples. As we scale to more finely discretized trajectories, the performance gap widens, with our method outperforming space-time constraints by between 90x and 180x. We performed this scaling experiment on trajectory D in our dataset, which was the trajectory where space-time constraints performed the best. We believe the pronounced performance improvement we observed can be attributed to our method having better convergence behavior. We see evidence of this claim in this plot. Here we show the total magnitude of the constraint violations for each method as a function of iteration count. Notice that our method is able to make very rapid progress in satisfying all of its constraints. In contrast, space-time constraints must spend significantly more iterations only to reduce the severity of its constraint violations by a modest amount. We performed this convergence experiment on trajectory B in our dataset, which was the trajectory where our method took the longest to converge. So, to summarize, we introduced a fast method for enforcing physical limits when designing trajectories for quadrotor cameras. We began by analyzing the quadrotor dynamics along a fixed path, and this led to a well-behaved optimization problem that could be solved at interactive rates. And finally, we found that our method was significantly faster than space-time constraints. In closing, I'd like to emphasize that this work is part of a broader research area that I am excited for all of us to explore. I believe drones are ready to be applied to many problems in computer graphics beyond capturing pre-scripted aerial cinematography. For example, teams of drones could be used in place of a gantry to capture complex spatially varying material appearance. In a similar spirit, drones could be used as camera arrays to capture very large light fields. The robotics community has already started to explore the use of drones for fabrication, which is already a central problem in computer graphics. And conversely, the computer graphics community has already started to explore the use of drones for designing the lighting in a scene. With drones getting smarter and more reliable every year, they are ready to make a big impact in computer graphics. There's lots of exciting work ahead, so let's get to it. And with that, I'll take questions. Thank you.
So we have time for a few questions, please.
Yeah, I'm David Geschwin. First, a quick observation. Using progress as your elastic variable seems really good in that post-production time compression can undo anything you need to do to make it feasible. My question, however, is given the mass of these drones and given wind velocity, have you considered the problem of dynamically adjusting for being blown off course?
Yeah, so great question, and it's an important thing to get right, because of course the trajectory that you sort of come up with offline cannot just be executed as is. You're always having to make constant adjustments to it. So I have not considered that problem super carefully. That is, in our current system and on most drones, that is handled by like a low-level, like a lower-level control system that's running on board the drone. I also think that like lower-level control problem is sort of has become commoditized, and so I'm excited. I'm especially excited about kind of the cool applications that we can build on top of a system that can sort of already control itself in the presence of unexpected disturbances.